laws of exponents, and we'll actually have one of these examples in our bell work, but in the meantime, we've got a couple of questions to explore real quick. Determine if the table is linear or nonlinear. So this is just a set of ordered pairs that have been put out in table form. So to find out if they are linear versus nonlinear, we just have to find out if there's a constant pattern going on here. So in the change in y, we go from -2 to -1. That's an increase of 1. From -1 to 0, that's a bump up of 1. And from 0 to 1, another bump up of 1. So in the y direction, we are going up by 1 each time. So that's a constant rate of change there. But that constant rate has to also be going in the x direction. So -10 to -5, increase of 5. -5 to 0, that's a bump up of 5. And 0 to 5, another bump up of 5. So basically what we're saying is this table has a constant rate of change of 1/5, or a slope of 1/5. And so that would be linear. All right, so next, write the decimal as a fraction. All right, so we've got 424. Oh, no, we've got 42. We've got to look at that. 42, 42, and 42. So we have the digits 42 that are repeating. And as we learned, instead of putting 42 over 100, we have to do 42 over 99. 2 digits that repeat, 2 nines that go under it for our repeating decimal version of a fraction. Okay, this next one, we have 7s that repeat after the whole number 5. So that would be 5 and 7. Instead of 7/10, that would be 7/9, because the number 7 is repeating. All right, we talked about some of this in our first section on multiplying exponents together. So we remembered that we have to multiply the coefficients. So 6 times 2 would be 12, and 12 times 3 would be 36. So our coefficients would amount to 36 when we multiply them together. Now we're going to look at the u's. We got u to the first and u to the second. So we're going to add the exponents. So that would be u to the third, because we're doing 1 plus 2. And then for our v's, we have 7 and 9. And 7 plus 9 is 16. And that's how we would simplify this expression as we multiply it together. So pretty nice. I like these exponents. All right, so today we're going to learn about a new rule for our exponents, and it's called power to a power. So basically, if we have 3 to the 4th power in parentheses and we raise it to the 3rd power, what we're saying is we have 3 to the 4th times 3 to the 4th times 3 to the 4th. And so if we follow the rule that we learned previously, when we're multiplying exponents, you just add the exponents together. 4 plus 4 plus 4 would be 12, which, if you think about it, is the same as multiplying these two numbers together. So 3 to the 4 times 3, which is 3 to the 12th. So you're basically multiplying the exponents together. So on this side, we're going to do, to kind of show the same pattern, w to the 5th times w to the 5th times w to the 5th. So we got to do it 4 times, right? So then when we add all the exponents together, w to the 5 plus 5 plus 5 and plus that last 5, we end up with w to the 20th power, which is the same as w to the 5 times 4 power. So when you raise a power to another power, you multiply the exponents together. So let's try it. 4 to the 4th to the 3rd power would just be 4 to the 12th power. because we're multiplying those two exponents together. Y to the second times y to the fourth would equal y to the eighth power. All right, so here's the rule. The rule is when you have an exponent raised to another power, you just multiply the exponents together. So x to the m times n is what we're trying to illustrate with this. So our examples would be x to the 2 times 3, or x to the 2 times 3 power, which is x to the 6, right? Or f to the 7 times 4 power, which would be f to the 28th power. I'm glad I don't have to write out all 28 of those powers. C to the 5 times 2 would be, or C to 5 to the second would be C to the 5 times 2, which is just C to the 10th power. So this is a pretty cool little rule. I hope you like this. All right, so raising a product to a power. So what if I have more than one thing in the parentheses? Like before I just had like an x or something to another power. But when you have more than one thing in the parentheses, you have to keep in mind each one of those things has a power on it. And if there's no power that they show, then you just put a 1 on there. And then you have to raise everything inside the parentheses to the power that you saw on the outside. So this would end up being 2 to the third power x to the third power. Now, if they wanted us to simplify this as far as we can, then 2 to the third power would end up being 8, and then x to the third power. Over on this next one, we would just end up with x to the second power, y to the second power, and that would be as far as we could simplify that one. So that rule was, whenever you have something inside of parentheses raised to a power, you have to make sure that that power gets raised to everything in there. So, and if there's no visible power, like if they don't have 2 or 3, you just assume that there's a 1. So that would be x to the m, y to the m power on the first one. The next one, x to the third, y to the third. The next one, j to the fifth, k to the fifth. Oh, and then the last one, r to the eighth, s to the eighth. So pretty easy rule to remember. All right, so let's try this one. So this one, you got an exponent of 1 on the 4. So 4 times 1 would be 4 to the 4th. And 4 times 2 would be 8, so w to the 8th. You got an exponent of 1 on negative 3, and the other ones have an exponent of 4 and 2. So 3 times that 1 would be negative 3 to the third, w to the 12th, and y to the 6th. So that would be how you'd figure that one out. So let's practice a few of those. Assignment number 33 on Alex, power to a power. Good luck.